So the integration was that we have been already calculating this. We want to calculate the area under a curve for some reason. It's to, some function, and we need to know the area under the curve. But no buts. We can do that by integration, the definite integral, like we did the last time. But sometimes you can't integrate the function. So you need this kind of numerical integration methods. And there is a couple of those, for sure. There might be even more. And then we would be using the Simpson's rule. I think I had maybe even a video of that, maybe. Yeah. So there's, well, this is just going through. There's the trapezoidal rule. So you can think that each little section here would look like a trapezoid, like they do in this case. And then you calculate the area of trapezoids. Finally, you calculate a sum, and you end up in this kind of whatever formula. Or then the midpoint of the rectangles with height taking at the midpoint of each interval. And then you have some kind of approximation again. Or then the Simpson's rule. And the Simpson's rule tries to model this with some kind of parabola. So the upper part here would be also a part of some parabola. So it's not either horizontal or some kind of a part of a trapezoid, but it's part of some kind of a parabola. And when you have this definite integral, you can approximate it with this kind of a formula. And this has been formed through thinking that this upper part would always be the parabola. So you have the first value, and then you multiply with 4 the odd ones and 2 the even ones, and then you still add the last. It uses parabolic segments for higher accuracy. Maybe most probably it's a higher accuracy to model the upper part of the, like this was in here. Maybe you get a higher accuracy when you have something a bit like curved here. And it requires even number of subintervals. So you have to divide this section into even number of intervals, but that should be quite easy to do. And then you just use the formula. It's very accurate for smooth curves and exact for cubic functions. So for example, something like this, you want to calculate the definite integral of, but you can't because you don't have the inner function derivative here. So you can't basically get the integral with the integration techniques, the integration whatever rules. And then you would calculate it with the Simpson method. And you just have to divide this area into, for example, four intervals. This is an equal number of intervals. And then you calculate the width of each interval. That would be this h. And then you get the function value with the first value x, function value with the second, with 0 first and fourth, and then you just calculate the approximation. And then you can compare it with the exact value as well. Yes, And of course, you can still make this interval smaller if you want even more exact value. But then you can also, for example, estimate like a cross-sectional area of a river with the distance from the shore and the depth. And the distance from the shore is measured, or you have the distance from the shore to 60 meters. So it would be distance from one shore, it would be 16 meters wide. And then you would have measured the depth. And you want to estimate the cross-sectional area, and you can do it with this kind of this Simpson method. And we will be practicing this also in this lesson. And comparison, well, here's a comparison, but we use the Simpson's rule. We don't need to. There's other methods as well. So it was the midpoint rule, trapezoidal, and the Simpson, I guess, is the best. Okay, I think that was all new stuff that we needed to maybe know, and we can just calculate. We can just continue calculating what we did the last time, and then end up into the well, I'll take this here for a bit. So we were here, integral, and I'll put, I'm not sure if all of these have a correct, like, sensible solution, but then maybe, I don't remember. But we had been calculating until here, maybe the 7, then we still could continue to determine the area of region bounded by these two, then the 9, and then we go to the numerical methods, which is the Noether method that we already know, and then the Simpson. And then there's a couple of Simpson exercises 3, where you can just use the formula. Hey, maybe I'll check if there was some decent video about this. This is the video.
What is Simpson's rule? The goal is to find the area under this curve within a definite range, numerical, meaning without using all those integration formula. To do so, we take samples of the function by dividing this range into equal intervals, where each interval is of the length delta x. Then we take 3 points spanning 2 intervals, approximate the function with a parabola passing through these 3 points, and find the area under that parabola instead of the function itself. Then we do the same to the next set of 3 points, and keep doing that till the end of the range of the integral. This might seem to be a bad approximation at first sight, but as we decrease the size of the interval delta x, the error considerably decreases. I'm not going to show the error analysis here, but check the description if you're interested.
So when you divide the area into smaller and smaller intervals, then the approximation gets more and closer and closer to the real value.
Now, how do we find the area under this one chunk? We can see there is a sum of the parabolic segment and the trapezoid. From the previous video about Archimedes' quadrature formula, it can be inferred that the area of this parabolic segment is 4/3 of the triangle formed by joining the 3 points. If you haven't watched the video yet, do consider taking a look.
Yeah, so
For more
there's
confusion,
for
let's
sure
keep
more
it
videos
very serious.
explaining this better. How you gain the full
We can write the triangle
how
as the
you
sum
form
of
the
two trapezoids, P1, P2,
formula.
PA, and P2, P3, CB, minus the trapezoid P1, P3, CA.
This is not really easy to follow, though. But now it's forming the formula.
And substituting the formula for the area of trapezoids, which is the average height times the base. For example, the area under the trapezoid P1, P2, BA is y1 plus y2 by 2 times del x. And the area under the trapezoid P1, P3, CA, which spans two intervals, is y1 plus y3 by 2 times 2 del x. And so we find the area under one chunk. Adding the areas of all the other chunks, we get the area under the function.
Why not?
And there it is, the Simpsons rule.
It was sort of decent. Video, I didn't check your page was what was the browns and blues.
Oh, yeah.
But for sure you have maybe more precise explanation of this there. I didn't actually check it. This was very quick. For sure you can get a better explanation. But maybe now we just accept that there's a formula that we can use. Yeah? Okay, you need your
Yeah. Yes, now I think it's easier for you to just pass.
Oh, yes, it's here.
Yeah,
It's not there inside.
yeah.
This is the thing.
I'm starting to trust this organization and this environment.
Don't trust this organization.
Okay,
Maybe.
only the environment.
Only the environment.
Yeah.
And so this Simpson method would be used in these three last exercises. So I think we have enough maybe to do for this lesson. Let's start doing the calculations.
I'm not so excited for this exam.
No, you're not excited.
We have a trip, a 12-hour car trip on the Sunday with the baby.
Okay.
So I don't know if I'm going to be rested or exhausted.
Before the exam, where are you going?
Sonia's going to some rugby.
Some what?
Rugby? No, the rugby.
Really?
She plays, or she was playing with the Finnish national women's team.
Oh, rugby. Aha.
It's the first-
Did she, oops, did she do this before she met you?
No, the
You don't even like rugby.
she wanted to try
Right.
people playing in Scotland.
Okay. So she played it when you lived in Scotland. She played rugby.
She tried it once, but didn't really.
Mhm.
do it.
Rugby looks so like there's these men piling up. I only seen it in the TV. And it looks like they are always trying to go somewhere, but they end up piling up.
Yeah.
You know, there's a big pile of men.
Yeah.
And you used to see the bums.
I don't know, I just never-
If it feels weird.
like in school we had to do, you know, where we gather around, it's like we're all done like this.
Yes.
So in school people just feel like maybe try to poke in that.
Oh, yeah, or somewhere else
Yeah.
in the testicles, maybe. Oh, horrible. Yeah, I never even been to a rugby game. For sure, that would be an experience. For sure, you in that kind of games, you are not allowed to poke people anywhere. For sure, they have to be really accurate about that.
Yeah.
Mm. But then it's good that the rugby is a sport for everybody because only the lightweight dudes can
Yeah.
play the football. But anybody can play rugby, yeah.
Yeah. And they have very nice though, like, or my memory of rugby is it's like very aggressive,
Hmm.
but it seems like all the ladies teams and Finland seem to be very welcoming and friendly.
Yeah, yeah.
But
That might be a nice like you get some like nice social group of people
yeah.
maybe when you have that hobby. Because in Finland that's not that easy to find some nice social groups of people. Or maybe it is, maybe it's just me.
I think it's hard, like,
It's more difficult maybe. It feels like I'm always saying some bad things about Finland. Don't take it seriously. You people who still have faith. Have faith. It's bad. Like I'm always asking, like, yeah, like yeah, it's like, and then you always say that I like it here. It's like, oh, okay. But why?
No, I think maybe that's just how it
Because
goes.
there's so much people, maybe it's so crowded. Yes. Mm. Yeah, I understand that. I couldn't live in a big city either. Obviously, because I'm from here, it's really difficult with like if it's really packed. And usually really expensive as well. Mm.
Feels like it's very common, like whenever someone moves to the UK, everyone asks like, why would you move in the UK?
Mm-hmm.
Like it's the worst place in the world. But I assume it's just, wherever you're from, you think, oh, this is the worst place, like everyone's there.
Yeah. I would definitely live in UK. Definitely, I would live in UK. But I would live in Belfast. Belfast is a sort of a town.
Yeah.
It's not a big city.
Yeah.
But I don't know how it's now. When I was there, it was lovely. It was a bit like Oulu, but there was a lot more going on, and it's just. But I also didn't have a family or kids. I just had friends, hobbies, beer, freedom. This is not how the life works. Fine, way then.
It's funny because all my friends from UK, if I think of, like my parents' age, they still, I feel like they drink every weekend.
Yeah, they are still in the same.
Yeah, but it seems appealing, like, now being able to just go to a pub and you're like, you've got mates to go with,
Yeah.
This year it feels more like, we'll plan it for 2 months in advance and then maybe everyone will go.
Yeah, and then everyone gets sick anyway.
Yeah.
Yeah, it's really difficult. And of course it's lovely, like in a culture where you can go in the pub and for 1 or 2, well, maybe even more, but maybe only for 1 and just chat a bit and just like do that regularly.
Yeah.
And then that's it. And you don't really have to the schedules aren't that tight.
Yeah.
Okay. So we were calculating this area bounded by curves. Yeah. And we found, well, we calculated, this is from the equation book, technical formulas. And then we went through these calculations, 2 of them. There was the 6 and the 7. Let's continue with the 8. Next. So if one would have ended up picking the wrong curve, because you have to subtract the curve from the one that's top, the one that's on the bottom. But if you ended up doing the wrong way round, you can kill the minus. This is where we ended up. So again, we are still in the area bounded or bounded by curves. there's still one more exercise at least of that. And in technical formulas, we are in the page 58. Area bounded by the curves. But then if these curves do this kind of like one is at the top first and then the other, then you have to do the integration by parts, basically. I don't remember, maybe we didn't have that kind of exercise here though. We just had like only one area. I'll still write the equation here. So the area is the integral from the beginning to the end. Then these what was it called? Absolute value signs here, and let's do the integral. And we now, of course, are assuming that it will be a function that we can integrate. So we are not yet using the Simpson's method. If my fx now would be the minus x plus 6 minus 8, and my gx would be minus plus 2. And then I have to decide where they basically, how do you say, like cut each other. So I would know GeoGebra. I would, for example, try the GeoGebra big as I can. So I put there the minus x. Oops, I seem to have x in the power of 2. Plus, have you been using GeoGebra or something like this on this course? Like when you've been doing, are you familiar using these kind of tools now? Okay. So it can be clearly seen that then you can write in the exam, but in the exam we don't use GeoGebra. It can be clearly seen that this is talking about this area now here, and this integral would be in the range from 2 to 5, and now we still have to calculate this. Then what else? It looks like this one is on the top, which is the parabola. And now, yeah, so this would go exactly the right way around. Well, no, yeah. Now I don't show this. So this is the parabola and this is the line. The parabola is on the top. So this would go exactly the right way around here as well. But let's now basically calculate the integration limits still. So it would mean that I know that they cut in the point where the value of y is the same. Yeah. Or there might be even many points where the value of the y is the same. This is, of course, like whatever x it is, it's the value of the y coordinate. So then I can write that, well, it's the same. Plus 6x minus 8 is minus x plus 2. And then I just arrange it all to the same side and mark it as 0. So for example, I throw these to this side. So I get a positive sign for this. So x to the power of 2. There's minus x, there would be minus 6x, so it would be minus 7x. There's plus 2, and then there would be, this would be plus sign, so it would be plus 10, and this is 0. And now, obviously, I can, maybe I have to take myself also the previous solution so that I can check that I'm not calculating something stupid here. So these solutions are also here, and I will take them to my other screen. So that we don't waste time for me calculating everything wrong. Okay, so because it's how do I always manage that? So this can be, of course, solved with the the second degree equation formula, or then I can just, I'll use the formula. How much time do we have? We have enough time. Whatever. So I get that this was the B, and it was the wolf. Maybe I need to check the formula as well. Plus minus. It's second power and minus 4 times. There's the A, 1 times the 10. And here, this is pretty easy. Here is 2. So my x is 7 plus minus. This is 49, yeah, and this is 40, so it would be a square root of 9 divided by 2, and I get like 3. So I get 7 plus 3 divided by 2, which is 5. And I get 7 minus 3 divided by 2, which is 2. And it looks like I got the same solution. It was pretty straightforward with that, even maybe faster than with my calculator. And then I start the lovely integration. So I will integrate. I will do this, exactly this thing here now. The area I'm calculating. Area from 2 to 5. And my fx was, now I get this with the different signs. My fx was this. And I have to fx here. There we go. Still a mark. So this is my, yeah, and I didn't write this absolute values in there. So this is obviously my fx. This. And then minus, and then I write my gx. Gx there. This is minus x plus 2. And that's my gx there. Does this seem clear to you? Yeah.
Fine.
Okay, ask.
See where it says minus x, where plus 6x, minus 8.
Minus x.
What happens, like, it's up above the, yeah, this bit. What
Here.
happens there? Yeah,
What happens here now?
yeah.
I just throw all the
The other side.
all the stuff to one side, but I wanted to throw these ones now to this side. So I have thrown all of these terms to this side and then just added them. And this is what was formed.
Yeah.
But I mark it the way that it was on this side, all the stuff.
Yeah.
And on this side, it was the 0 because this is the way I'm used to do it. This is the way you usually have it. Yeah.
Sorry, thank you.
Yeah, no problem. Just ask if you're thinking about something. So now I have to add these together. I get minus x in the both. Then I have to add 1x, so it would be plus 7x. This is exactly the different, it will be exactly the different signs as I had here when I wanted to have this positive. But of course the roots, if the parabola opens downwards or upwards, are the same. It just opens a different way. But here I'm only interested about the roots, basically. So I get like, if I have here opposite signs to this, for example, even if it now doesn't make any difference, but I would still, which way I would do it, I would get the same roots, but I would get it either opening upwards if the second degree term was positive, and if the second degree term is negative, I have it opening downwards, but I still have the exactly same roots. Yes. Yes. Did I mark the dx? The dx is important. And now I can go through the integration. So I have 3, and then I have, this. And then I can start putting the values where the x is. So I have to put the end of the first. This doesn't look that nice. Minus 10 times 5. And still I have to subtract this with the value 2. It still doesn't look nice at all. Why did I ever want to do something like this? So now I can try to make it look a bit nicer, or then I just put it in the calculator. Ooh. So, this is, maybe I just put it in the calculator. I don't want to start doing this like this. Does it make any sense? Am I gonna get it anything nicer? No, it doesn't look like it's gonna get anything simpler. I just put it into the calculator. Thanks. No, I don't want to do it. Well, this is maybe 50. And then I get plus. No, I get the different sign there. I should have put the brackets. I have to go and change that. Minus. And here I get a plus. I can hope for the best. Oh, but oh, is this true? I have got something different the last time. Yeah. Do you like calculating something like this? No, because it's easy, really easy to get something there. Some kind of problems. Or 11 times. Yeah, here I have I have a wrong power. So this is not 4. This is this is and then it gets a different sign. No, it doesn't actually. Yes, it does. No, this is still that sign. It's not inside that thingy. So this is 8. Ha. I got the same result as the last time, so I'm happy. Maybe this is not something that we are practicing here. We're just practicing this, but then if in the exam you happen to get something like this, it would be good to be able to put it into the calculator the correct way. Illustrate with the figure, whatever. So you want to round some, this is some kind of application function. Y is fx. Maybe y is x. Y is fx. No. Y is x. Yes. So we want to rotate something. Y is x. So we want to rotate the line. Y is x. Which is the simplest line that you can have. Which is this. This is, of course, the y is x. line and we want to rotate it around the x-axis over some interval. The volume of the resulting solid is calculated using this kind of a integral. But okay. And a cone is formed. Calculate the volume. So you can calculate the volume. Why did I draw it here? It's not like I'm talking about this anyway. Well, that was the line. I'm rotating it. So I have a line y is x. And this is, of course, my fx. And I want to rotate, I want to calculate a volume for my rotation, and it's being calculated with this kind of a formula. In the power of 2. So I have to put this in the power of 2. My fx is x, so my fx in the power of 2 is x in the power of 2. And then I just have to form the integral and calculate it from in a range of 0 to 10. It sounds a bit complicated, but for sure, yes. The actual calculation is super simple. And then I just calculate this. And then with the 0, so I get like 1000 p divided by 3. Something. So it was, so I wanted the area volume of something that I'm rotating that line here from 0 to 10. So obviously there's some kind of a cone here where I calculated the volume of something like this. It was rotated there. And this is a stupid exercise anyway. But obviously there's some kind of application. Yes. Whatever. And the volume is something like this. And this is in basically cubic. Was there some? There wasn't even any unit cubic squares, cubes of this size. Yes. So that is my unit. Yeah. Whatever.
Nicer than the last one.
It's nicer than the last one. Yeah. Well, it's at least it has maybe some meaning. Okay. So then numerical methods, Newton and Simpson, and then there is now one to be done with the Newton method. The region is bounded by these kind of curves. And now you should calculate the area of the region. But you can determine the limits using Newton's method. And why is that? So let's take the curves. Well, I'll just write, for example, fx and gx. I could mark them like that. Gx 2 minus e in the power of x. Let's try to draw this with the GeoGebra then. So I would have x in the power of 2 minus 2x. Let's put these away. And the other one would be 2 minus e in the power of x. Like that. So there would be the area that I'm trying to calculate now. But then the integration limits, I know how to get them. And the integration limits would be, of course, so I have this what was it? System of equations. So my x in the power of 2 minus 2x is when they cut, they have the same y coordinate, obviously, and the same x coordinate as well. So here I'm calculating that where these lines would have the same value of y, same y coordinate, or same value of the function with the certain x coordinate. So obviously the same x coordinate as well. And now if I would want to calculate something like this, I could throw either to the either side and try to start calculating. I would have plus e in the power of x minus 2x minus 2, this 0. And now I can't solve this, can I? So I can't, I don't have some formula that I could use for that. No, because there's this damn thingy there. Yes? So now I could use the Newton method to get, do you remember the Newton method? We quite frankly went through it.
Yeah, I don't think I could apply it, just a problem that makes where something.
I would say that no formula or something like this. Formula is also the milk for a baby. Newton method. Newton's method. And where was the formula for Newton's method? In this, it was in the differential calculus. Where is it? Did I manage to find it the last time? Or already in the integral calculus. What was it called? here. Haha. There. So we have some kind of a curve. So the curve here would be now mix it up. Plus minus was it minus 2. Let's put these away for a bit. It looks like this. Quite an innocent looking curve. But how to get these points here? Okay, so we could take a guess. We can decide what we guess from here. We guess half, minus half. Guess, I guess minus 0.5 and 1. Half and 1, yeah? And Newton's formula equation I found. So it's from the technical formulas page 45, and it is xn plus 1 is xn minus fxn divided by the derivative, that. And now the thing that I need, my fx is this, yeah? X in the power of 2 plus e in the power of x minus 2x minus 2. My derivative is 2x plus e in the power of x, because it was its own, minus 2. Yes. This is all I need. And then the initial guesses. And then I take the Excel. Because I'm not going to start calculating something like this by hand. Okay. And if I want to write this now here, I just put it there. So my guess, let's put like this is, for example, my x0 is, for example, minus 0.5. This is how the Excel processes it. My second value is I write the equation, this. I wonder what it will finally be. Yes, minus, and then I write my function. So it would be this. Oh, I have to put the brackets first for sure. So it was this in the power of 2. Plus, what did I do? Okay, did something wasn't correct. No, yeah, because I jumped out of it somehow. So for sure you are really experienced already to how to write things with Excel. Exp is my yeah, exp. And there I can put again the same thingy. That's my exponent. And then minus 2 times the same thingy. Minus 2. And close. Divided by. Up the brackets. Do you feel experienced using the Excel like this?
Yeah.
This is not difficult for you at all. Exp. For me, it's more. Come on. Take it. That. Minus 2. Close. And I get the second value. And then I just drag it. And it looks like from the next value on, it's the same. So that must be this. Then my other guess was 1. If I copy this here. No. There's something completely different. Why don't you copy it? No, I'm doing now something weird here. I have to copy it from here, yeah. To get it here. Huh? But then I just have to put the B2. Why did it want? Oh, false. Don't. Just whatever. Can I just drag it? Huh. I can just drag it, yeah? I don't have to copy it. No, but do I do something weird now?
Fill the
Yeah, I could just, of course, I can just drag it. I don't have to copy it. And now I get everything. That's it. Yes.
You do this without, you know, when you're doing this with Excel, Newton doesn't have Excel. So he has to just calculate every one of those points.
Who doesn't have?
Newton. No, if it's Newton,
Ah. Yeah.
you just ask
How frustrating is that? So what I can do now is just to do the integration, yes? Now I'm able to integrate anyway. So I know now what are my my guesses, and they ended up being, I'll write the correct ones here. So they ended up being minus 0.5994 and 1.103638. And now I can do the integration. So again, I do the area. So I integrate from 0.55 something to 1.10 something. And I integrate the whatever. There was just one area. So just one area with like no, you know. So I can have either of being fx and either of gx, even if I could even, but it doesn't make any difference. I have that one as fx. I could check from the which was on top and which was on the bottom. Minus gx so that was my, like there, the fx and gx. Then, so I do the integration from about whatever to whatever. DDD. I don't write those, how many, those decimals there. Minus whatever 2x minus 2 plus e in the power of x. I have it in a bit different order here, but it looks exactly the same. Otherwise, I forgot the dx there. Oh, dx. And then just do the integration. So I get the range from to DDD. And here is power of 3 divided by 3 minus 2x in the power of 2 divided by 2 multiplied by 2, so x in the power of 2 minus 2x and plus e in the power of x, because it was its own derivative or integral. And then I just stick the values there. Would I like to do it in Excel or somehow? I would do it in Excel. I don't want to do it with the calculator. So now I calculate the area. I mark it here. And it is well, let's take the last. So I go until here, this in the power of 3 divided by 3 minus this in the power of 2. Maybe I could have put this in some better place or something, but I don't know. Minus 2 times this again plus x with this again. This is my, and then I have, from this I have to diminish the starting this same function with the starting point. This was the starting point. I could maybe somehow copy it or something. How to do this easier way. Exp with this. And that's it. The bracket. Ooh. Yeah. And now I get this. So obviously I had them in the wrong order, but I can always kill the minus. That's my area, but I need the absolute value of that. So let's pretend I calculated it. I calculated it with Excel because it made sense. Otherwise, it would have been really frustrating. And then I just kill the minus. And maybe round it a bit, 1.28. And that's it. And then I can compare it with what I did with the GeoGebra. Here. About 1.3, this area. It makes sense, yeah. About 1.3. Why would I want to calculate something like this? But this kind of numerical methods are being used in all of the programs that you use. They don't have any values for certain integrals or whatever. They can't calculate the roots for certain functions any better. They use the numerical methods. So now you know that what kind of methods they would use. Like we would also see that with this Newton method, we got actually really exact roots when you keep on iterating it, calculating it over and over again.
Where would we use, like the graph, when we use that, like, what would that come from?
The what?
You had the graph when it goes like
graph, yes.
And then the one goes this way.
Yes.
What would the overlap be? Like,
what would the area be?
Yeah, like what could it? If I had...
it could be anything, but I don't know, something that you model and then you want to get the common. I don't know. It would be nice to have some examples. You didn't have anything like this in the physics, did you? Maybe in the following years you will have something like this.
Yeah.
Hopefully.
I was wondering if it was space, because I've been watching the thing that's went to the moon.
Yeah.
And I was wondering if it's like, if there's a ship, like a spaceship going, and then if there's like something floating, if it do crash into each other. But I don't know. Yeah, okay. Why not? For example, something like this, you have to know if there's something floating in space, that the spaceship doesn't catch the poor spaceship. You just put the spaceship there and then you have to calculate where the other particles, if there's something moving there. Okay, Simpson's rule.
There's still a couple of calculations to go. And now we would want to calculate the approximation of a definite integral of something like this that we can't again integrate with the integration formulas because we don't have the derivative of the inner function. So we would need to calculate the value of the integral with Simpson's rule. Does this seem any way sensible to you? The Simpson's rule we could find, and for sure the teacher, the great maths teacher that even did its own graphics itself and even coded them, can tell you about this Simpson method with a great accuracy for sure. I have to put those videos links there as well for the next ones. Simpson formula is Simpson's rule here, 58. Simpson's rule. Da-da-da. This was, now I'm starting to lose the ink of my pen. This was in technical formulas, page 58, and it looked like, wow, it looks pretty long. So you have to know the, like, you have to divide the area into sub-intervals, basically. This is what this means. The h is the width of the sub-interval. It has to be even. Then I'm integrating from A to B. So this is the range that that's my integration range. Something that I can't integrate with the integration rules. So I use this kind of a great approximation formula. So I always multiply with 4 and 2. The odd terms with 4. Well, the odd. And so on. 2 times the next. X4 plus. Ding, 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 ding. Until the end. And then I have to add the last. Okay. That was the Simpson's formula. And my function is this. I want to calculate the definite integral of something like this that I'm not able to integrate with the integration rules. Most probably I would like to do this with the Excel as well now. Then these ones are actually easier than just, you can calculate by hand as well with the Excel as well. For this is a bit maybe. But yeah, but if I have only 4 intervals, 4 sub-intervals. So my sub-intervals would be, I go from my x would be from 0 to 1. I divide that area in 4 sub-intervals, so I would have 0.25, 0.5, 0.75, and 1. So my first interval is from 0 to 0.25, second, third, and fourth. And then I would need to have the values here. So my age, first of all, if I write the age here, is my 1 minus 0 divided by 4. So 1 divided by 4 was 0.25, yes. So then my fx with 0, my fx is this. So if x is 0, then this is 1. E in the power of 0. Then I have e in the power of 0.25 in the power of 2. Ooh. Why couldn't I calculate it with this as well? Maybe I can. No. This. And then I put there 25 in the power of 2. Wow. Maybe it's not that easy to calculate which is something. And then I have to, so this is my x0, f with the x0. This is the x0. Then the f with the x1, x2, and x3, x3, and x4. I think I would calculate this rather with Excel. I'll just put it into the Excel. Now I'm already frustrated after doing this. No thanks. What did I do with my previous Excel? It's somewhere there, maybe. Book 1. Whatever. Next. Okay. So how do I write it here?
I go from, I have just decided. I could have calculated just here, whatever, like, is, yes, I could have put the range here, which is from 0 to 1. Then my thingy here is with this, so I can calculate anything minus this, and I want the 4 subintervals divided by 4. I get 0.25. Then I start from this, and I put here the 0.25. This plus this, and then I just add it until 1. No, I wasn't successful. Whatever. What did I do wrong?
Can you go to the cell then? So go to.
I did what did I do now?
You go, yeah, highlight it.
I just added A1 this, C1. Yeah, because it wants to do that. I want to do, I'm not adding anything there, am I? If I put it like this, no?
Oh, if you go to A1 and press, and then
A1,
that, oh, A2, sorry, the one below,
hello?
and then on the formula, press.
I put the dollar marks.
Yeah.
Where do I get there? The blah, 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 blah. Does it go like this?
Yeah.
And in the correct spot?
Yeah.
No? And then I do it. Da, da, da. So I didn't have to do anything like this. I don't know what I did there. Just how do I delete it off? Delete. Thanks. Next. Now I got this. It's not going great. But then, oh, here is even 1. Look, it's even the same. But now I have to put here that it's exp. And here I have to put the thing. And I have to put it into the, like this. Ha. Now I got it. Wow. And then the damn formula is. And now I put here this divided by 3. That's the formula. Times. And then in the brackets. And then it's the first. Plus 4 times the second. Plus 2 times the next. Plus the last. So I didn't have more than this now. Did I take the first? I didn't. I took the wrong, did I? No, I took it. No, I took the B2. I should have taken this. Oh no. B1. B2. B3. Then I have to put the B4 still. 4 times. Plus. Oh. Okay. And this is my area. And now I still check from the GeoGebra. So my function is a in the power of x in the power of 2. And I was integrating it from 0 to 1. So it's this area, and it's supposed to be it's supposed to be 1.46. So it's this area here. So it makes sense, doesn't it? Because this is not quite half. You get a little bit more. So it's about 1.5. 1.5, 1.5. Yes? How nice is this? Okay, so there were still a couple of exercises. We could check them in the beginning of the recap.
Yeah.
You could do those with the Simpsons rule. It's not gonna maybe be this frustrating because you're better using Excel. Or maybe they can be even easily calculated by hand. So that we can consider if we can have similar in the exam.
Do you have the question revision already or?
No,
Okay, thanks.
I will have to do them tomorrow.
Would you be able to, like, if you have time, could you put them back if they're them at the weekend?
Yeah, before, yes. I will put them there. So first I have to decide how the exam is and then do those. But for sure we can, and I think we had in the exam in what that was in Finnish, we had some Simpson exercise with the written like those ones that will still be there because it was pretty easy to calculate by hand as well. So I will try if that's very frustrating,
Yeah.
or then if it's not super frustrating, then we can put one like that as well.
Yeah, yeah.
Okay, so what do you think about the course now? I will do the recap for the next week. And after next week is, okay, tomorrow. I'll put it there. We go through it next week, and then the week after we have the exam.
Yeah.
Yes.
Nice.
So how do you feel about it?
Yeah, apart from the trip, I think it would be okay.
Mm-hmm.
I just worry about like.
Not too bad.
What do you think? The exam.
Mm-hmm.
Henrik says to me, everything we have with the exam, Henrik says, oh, I don't feel